This is a brief introduction to the EasyAmp project, quantum realisation of the SI ampere, funded by Euromet, the European Association of Metrology Institutes. The ampere is the SI unit of electrical current. It's one of 7 SI base units. These define quantities of electrical current, length, time, mass, luminous intensity, temperature, and amount of substance. Taken together, the base units can be used to define other quantities. So the meter and the second can be used to form a definition of acceleration and velocity. Add the kilogram, and power, energy, and momentum quantities can be defined. Add the ampere, and electrical and magnetic quantities are defined, such as the volt or the Tesla. The base units underpin the entire measurement system. They sit at the top of the calibration chain, both for the quantities that they define directly and those derived from the base units. Each of the base units has a formal definition and a method of realisation. The definition of the kilogram is that it is equal to the mass of the international prototype kilogram, a unique object. In other cases, complicated experimental apparatus is required to realise the conditions for some fixed point in the measurement system, such as the triple point of water in the definition of the Kelvin. These definitions are not necessarily considered to be the best ones. For instance, there is particular criticism of the definition of the kilogram. It is a unique artifact, so it cannot, by definition, be reproduced. And how do we prove that its mass is perfectly invariant? Realisation of the ampere also looks rather impractical. It involves measuring a mechanical force between current-carrying wires. Now this means, because you're measuring a mechanical force, you need to rely on the other units, including the kilogram, with all of its associated problems. On paper at least, it also calls for infinitely long wires. Research in solid-state physics has provided us with quantum mechanical effects, which enable voltage and resistance standards to be found which are very reproducible, and these do not rely on mechanical experiments. Electrical metrology has moved on, but the definition of the ampere has not. Now, to help with our definition of the ampere, we should consider what electrical current really is at a more microscopic level. It's the movement of charges, normally electrons. Now, one thing we do know is that the charge on each electron is fixed. The precise number that we associate with its charge depends on the unit system, but it's definitely identical on every single electron. So the thing that we don't know is how many electrons per second are flowing through the circuit. Is this something that can be controlled? If we could control the flow of electrons through a circuit one at a time, then this would form a very stable current source. And as it's based on counting, it would be very accurate and the kind of thing that we would like to use to replace the present definition of the ampere. This is the essence of the EasyAmp project. We would like to turn the idea of a single electron pump into a real metrological tool that national measurement institutes can use to realise the SI ampere. Now this requires lots of project partners with lots of different skills. Our project is based around a consortium of partners from Europe and beyond, bringing a broad range of technical capabilities. One thing we need to do is to build semiconductor devices which can be used to trap single electrons and then release them. We want to do this repeatedly, at high speed, very accurately. Then we need to examine the devices very carefully, to study their output to find out whether they're behaving exactly as they expect. This electron pump should be pumping precisely 100 million electrons per second, giving this current. But how do we know there aren't any errors? Our work on improved current standards will have an impact outside the community of national measurement institutes. There are several examples where small current traceability is very important to people's applications. In radiological systems, ionisation chambers are often used to measure radioactivity levels. Here, small current traceability is vital. Aerosol particle counters also are used to measure small currents, and this is a realm where electron pump calibrations might be useful. Technical work on our progress and techniques will be released in other videos. In the meantime, you can find more information about our project on our website.